So next is energy bands in solid. From Bohr's atomic model, we know that the electrons are the electrons have well defined energy levels in an isolated atoms. But due to the interatomic interactions in a crystal, the electrons of the outermost shells are forced to have energies different from those in isolated atoms. So here each energy level splits into a number of energy levels, forming a continuous band that is called the energy band. Now if I take a small single crystal of silicon, I can see that it has n atoms. Now these atoms are being brought closer from infinity so as to form a crystal of lattice spacing, that is 2 or 3 angstrom. Now if I plot a graph in which interatomic spacing is plotted along x-axis and energy along y-axis, I can see at a very large interatomic spacing there is no interaction between the neighboring atoms. All the atoms have identical, all the atoms have identical energy levels. Now as the interatomic separation decreases, now the valence electrons of the neighboring atoms begin to interact, and the gap between 3s and 3p, this 3s that is the outermost shell, 3s and 3p levels completely disappear and the upper level and lower energy level merge with each other. Now at a equilibrium separation, we can see that the band of field energy levels get separated from the band of empty energy levels by a energy gap. So the highest energy band filled with valence electrons is called valence band. That is the uppermost energy band which is filled with valence electron is called your valence band. And conduction band, the lowest unfilled allowed energy band next to valence band, is called conduction band. It is the lowest unfilled energy band. It is the next to your valence band, is called your conduction band. And the gap between top of valence band and bottom of the conduction band, in which no allowed energy levels for electron can exist, is called your energy band gap. Now depending on the energy band gap is 0 or large or small, the solid may be classified into metals, conductors, insulators and semiconductors. Here in case of metal, there may be two conditions. Either there is a energy gap between the filled valence band and the partially filled band. There is a gap, means there is a small gap between the valence band and conduction band. We can see the example in case of lithium, sodium and potassium. There is a small gap, or the conduction band in the second case, or the conduction and the valence band partly overlap. The examples are in case of beryllium and magnesium. Now in case of insulator, if the energy gap is greater than 3 AB, the energy gap is very large, greater than 3 AB, maximum is 6 AB. That is, we can see in the case of a diamond. So diamond is a very bad conductor. Now the third is semiconductor. So in semiconductor, we can see if the energy gap is less than 3 AB, so the energy gap, we can see the example of silicon, that is 1.17 eB, and for germanium that is 0.74 eB. So in semiconductor n-type semiconductor, a very small energy is required to free the electrons from the donor impurity. So the donor energy level, that is ED, that is here it is AED, lies just below the bottom of the conduction band. So at room temperature, this small energy gap is easily covered by the thermally excited electrons. So the conduction band has more electrons than holes in the valence band, as they have contributed both by thermal excitation and donor impurities. In the case of p-type semiconductor, what happens here, the acceptor energy level, that is EA, lies just slightly above the top of the valence band. So at room temperature, many electrons of the valence band get excited to the acceptor energy level, leaving behind equal number of holes in the valence band. So these holes can conduct current. Thus the valence band has more holes than electrons in the conduction band.